Students. So let's solve the question number 3. Okay, so the question is, an entrepreneur has the production function Q is equal to A x1 to the power alpha x2 to the power 1 minus alpha. So the question here is given by an entrepreneur has the production function Q is equal to A x1 to the power alpha into x to the power 1 minus alpha. Okay, so she buys, as per the question, she buys inputs and sells the output. She buys inputs and uh, sells the output at fixed prices. Okay, but is subject to a quota which allows her to purchase no more than x1 to the power 0 units of x1. Okay, so but is subject to quota which allows her to purchase no more than x1 to the power 0 units of x1. Okay, so she would have purchased more in the absence of the quota. Okay, so because of quota, she is reducing her purchasing quantity of the purchase. Okay, so she would have purchased more in the absence of the quota. Now we have to use that as per the question. They've asked that we have to use Kuhn-Tucker analysis to determine the entrepreneur's condition for profit maximization. So the question is, use Kuhn uh, use Kuhn-Tucker analysis to determine the entrepreneur's condition. Okay, uh, for profit maximization. Now, question is again that what is the optimal relation between the value of the marginal product of each input and its price? Again, the question is what is the optimal relation between the value of the marginal product of each input and its price? Okay. And the third question is what is the optimal relation between RTS and the input price ratio? RTS and input price ratio. So we have to deal with these questions. So let's solve it. At first, the profit maximization problem subject to the quota, we can formulate it in this way, in the traditional manner. So let me change the color of my pen. So in the solution section, So the profit maximization problem subject to the quota can be formulated as maximize profit, that is equal to PQ minus W1 X1 minus W2 X2. Okay, and the constant equation is here, that the subject to function is Q is equal to A of X1 to the power alpha and 2 to the power 1 minus alpha, X2 to the power 1 minus alpha. So A X1 to the power alpha into X2 to the power 1 minus alpha. Okay, so this is the constant function, and also given that x1 x lies between x1, so x1 is less than equal to x1 to the power 0. Okay, so and also the other condition is given here as x1 is less than equal to um, x1 is less than equal to x1 to the power 0. So here, so where T is the output ratio and W1 and W2 we have assumed here as the input prices, and x1 to the power 0 is the quota, it is given there in the question. So where is given that P is the output price, W1 and W2 are the input prices, x1 to the power 0 is the quota restrictions. This is given. So now we have to set the Lagrangian problem for this problem. So to solve this by using the Lagrangian method, so we have to set the Lagrangian for this problem. So the Lagrangian uh, for this problem is L is equal to PQ minus W1 x1 minus W2 x2 plus lambda of E x1 to the power alpha x2 to the power 1 minus alpha uh, minus q plus mu of x1 minus x1 to the power 0. Okay. So here we have considered that lambda and mu are the Lagrangian multipliers for the production constant and the quota constant. So we have used here that where lambda and mu are the Lagrange multipliers for the production constant and the quota constant. Okay. Now we have to differentiate it the first order with respect partially with respect to q. So if we differentiate it with respect to q, so the first order conditions are, that is FOC, that is delta L, delta Q. It can be written as P minus lambda is equal to 0, right? Now delta A with respect to, if you differentiate it partially with respect to x1, you will find that W1 plus lambda A, sorry, it should be written as lambda alpha into A x1 to the power alpha minus 1 into x2 to the power 1 minus alpha plus mu is equal to 0. And similarly, if you differentiate this Lagrangian function with respect to x2, you will find delta L with respect to delta x2, that is equal to minus W2 plus lambda of 1 minus alpha into A x1 to the power alpha into x2 to the power minus alpha, that is equivalent to 0. Okay. Now it can be written as A x1 to the power alpha x2 to the power 1 minus alpha is equal to q. Okay. And also it is given here that x1 minus x1 to the power 0 is less than equal to 0. Okay. Again, I can write it as mu of x1 minus x1 to the power 0 is equal to 0. Okay. So here we're converting this that the complementary slackness conditions. So we have to apply these the Kuhn-Tucker complementary slackness conditions. So which are, let me write it as the the Kuhn-Tucker complementary slackness conditions are uh, mu of x1 minus x1 to the power 0 is equal to 0. Lambda is greater than equal to 0 and mu is greater than equal to 0. Okay. Now using these conditions, we can solve the optimal input and output level, right? So using these conditions, we can solve the optimal input and the output level. So we can write it as x1 is equal to minimized form of x1 to the power 0 and w1 by lambda a into a whole to the power 1 by alpha minus 1 into x2 to the power alpha minus 1, and it's covered with 4 brackets. Okay. Now again we can write x2 as W2 by lambda of 1 minus alpha into A whole to the power 1 by alpha. Okay. And the Q is equal to A into x1 to the power alpha into x2 to the power 1 minus alpha. Here. So now the optimal values of lambda and mu can be found by substituting these expressions for x1 and x2 and q into the first order conditions, right? So the optimal values of lambda and mu to the optimal values of lambda and mu can be found by substituting this expression for x1 and x2. Substituting these expressions for x1, x2, and q into first order conditions. Okay. So the optimal relation between the value of the marginal product of each input and its price can be established here. So now the optimal relation between the value of the marginal product of each input and its price is, so we will use VMPL. Okay, so VMPL 1 by W1 is equal to lambda A x1 to the power alpha minus 1 into x2 to the power 1 minus alpha. And again, VMPL2 by W2 is equal to lambda of 1 minus lambda A x1 to the power alpha into x2 to the power minus alpha. Okay. So the optimal relation between the RTs and the input price ratio. So we have to establish this, the optimal relation between these two factors. So the optimal relation between RTS and the input ratio is, so RTS is equal to minus D ln x2 by delta ln x1 is equal to minus 1 by alpha divided by alpha of delta ln x1 by delta ln x2 is equal to W1 by lambda alpha A is equal to W2 by lambda into 1 minus alpha into A. Okay, so this is the solution of this problem, and watch the complete video and you will get the solution of this problem. Okay, so thank you.